Hi guys, here is your second video, and I just want to remind you that the book solutions are on School Loop, as well as some selected worked out problems should also be up on School Loop. So if you need to borrow an iPad to check solutions, that's totally okay. And then we're going to push on. Hopefully you have your notes in front of you. And we're starting in on section 9.4. So this one is all going to be about chords and how they are related in a circle. So the first one kind of makes sense. If you have congruent chords, then that means these chords, so they're the same length, which kind of makes sense that if they're the same length, the corresponding arc that is swept out by them should also be the same. And the converse is also true, that if you have two arcs here that you happen to know are congruent, then the chords that would go across those arcs will also be congruent. So it works both ways. So basically you can say that congruent chords, if and only if you have congruent arcs. Okay? Another important theorem, so again, I hope you guys are keeping a reference sheet as we start building a lot of these different properties. So this one also, if you have a diameter, and of course a diameter is just the full, line here, so you can also then just have a radius. If that radius is perpendicular to a chord, so again, you have the radius, it happens to be perpendicular to a chord, what happens is the chord gets bisected, and since the chord is now bisected, so is the corresponding arc as well. Alright? So this also works in reverse. So if you have a circle and you have a chord and let's say a line like this, and you happen to know that this is congruent, then it will turn out that this is also going to be perpendicular. Okay, so a lot of these work both ways, and that of course also means then that these two arcs will be congruent. So the applications for that are going to be huge. So we're going to be able to create a lot of right triangles, which means you're going to be revisiting a lot of your right triangle trig. So this first question, find the value of OE and AB if OA is 6. So another way of giving you that information would be if I said that the radius of this circle, of circle O, equaled 6. So we know the radius here is 6. And we know AOE right here is 60 degrees, which means we have a perpendicular here that we know about. This is a 30 degree. So I know that OE is going to be half of the hypotenuse. And we know AE is going to be 3 rad 3. But what it asked for was all of AB. So what we do is we just double that. So you have 3 rad 3 plus 3 rad 3. So AB will end up being 6 rad 3. But this brings us to a point that I want to point out two things that have happened so far. Always draw radii to two possible positions. One, to the end of a chord, because it potentially creates a right triangle for you, or a triangle of some sort, or, as we've talked about before, to a tangent at the point of tangency. So drawing those lines, whether they're there or not, will often allow you to solve a problem. So if you want to pause the video for right now, on this page and the next page there are 9 problems, and if you want to take a minute and try and do them, that would be great. Otherwise, I'm going to go ahead and start solving them for you. So you can either turn the volume off and then look up, or I'd rather just pause it and then we can play it through and make sure we have the same answers. So on number 1, we're going to draw the radius to the end of our chord. Since it's perpendicular, I know this little piece is 12, so I have a 5, 12, 13 right triangle. Over here I draw my radius to the end of the chord, so I know this little piece is 3. I do not have any kind of a special triangle. I'm going to just have to do my Pythagorean theorem, so 3 squared plus 6 squared is going to equal 45. So that represents my radius squared here. So we know our radius is going to be, that's going to be 9 times 5, so 3 rad 5. On number 3, we draw the radius to the end of the chord, not necessarily the friendliest numbers, so this will be a 5 halves. So we have to do our Pythagorean theorem to find our radius, so we have 2 squared plus 5 halves squared will equal the radius squared. So we have 4 plus 25 fourths. So what that means is we need a common denominator. So this will be 16 fourths. That equals 41 fourths. That is our radius squared. So square rooting that gives you a radius of square root of 41 over 2. Continuing on with these problems, sort of in the same vein, on number 4, we know that this will be 4, it's half, so x will be 3. We have a 3, 4, 5 right triangle. Here notice that this random chord, or sorry, this random radius out here is 3, so what we want to do is draw that radius to the end of our chord, and 2 represents this length right here, the distance to our chord. So I know that 2 squared plus, I'm going to just call it y squared, we'll call this little piece y, is going to equal 3 squared. So we have 4 plus y squared equals 9. So y squared is 5. Y squared is 5, so we know that this little piece represents the square root of 5. So all of x, sorry, I don't know if you can hear dogs barking in the background. I'm sitting out in the backyard. So the whole thing is x equals 2 square root of 5. Okay, then we get to number 6. Basically this one, we actually haven't talked about this property yet, so I'm going to talk about it now, but it's coming up in a slide. That notice you have 2 segments here that are congruent, and so that means that these chords are equidistant from the center. Well, if they're the same distance from the center, then that means that they are going to be congruent. So each of these x's will be 3. So think about it. If I had a longer chord, that means I would be closer to the center of my circle. So if the chords are equidistant from the center, then they must be congruent. Number 7, we are going to drop a perpendicular, which we know bisects our chord. That means it all 60 degrees. So I know that the distance here will be 6 based on our 30, 60, 90. This distance right here will be a 6 rad 3. And so all of x will be twice that. So x will equal 12 rad 3. Now, this one, very interestingly enough, so 86 represents just this arc here. So that means this angle right here is 86, which means this angle right here is going to be 180 minus that, which makes it 94 degrees. So you have a triangle here. I'm going to draw it a little bit bigger. And so I know that this is 94, but what I'm going to do is I'm going to cut that in half. Here's x. This will become 10. I dropped a perpendicular here. Half of 94 is 47, so you're going to have to use your right triangle trig to figure out x. So we know, since this is opposite and this is hypotenuse, we'll do sine. The sine of 47 is the opposite over the hypotenuse. And so you'll reverse this, x equals 10 divided by sine 47, and that should give you an answer of 13.67. And then last but not least, we have this triangle in number 9. Notice that the radii are always congruent, so you want to kind of give yourself a visual marker of that. So I have an isosceles right triangle. That means these are 45-degree angles, so this will be 6 rad 2. Okay, now we have that property that I was just talking about. So you have 2 chords that are equally equidistant, and again, remember we always measure distance along a perpendicular, so that means that is like this. That means we also then have 2 chords that are congruent, and because it's along a perpendicular, these segments are also bisected. And because these two chords are congruent, so now you start to see everything kind of folds in on itself. Since those chords are congruent, we also know these arcs would be congruent. And then you can also go vice versa. If I start with the chords being congruent, then I can conclude that they are equidistant along a perpendicular. So I could draw those perpendiculars in there. So an application of that would be, so I have a two perpendiculars here, and if this is 3, this is 3, so that means I have two congruent chords, which means I know that they are both equidistant from the center. Another problem that I kind of want to give you that relates to that is if I give you these 3 chords here, so you don't have this one in your little set. Obviously go by how I mark it, not by how it looks. And this is 120 degrees. Let's call this x. Find x. And don't just say there it is. Okay, so how would I do this? Well, I know all the way around the circle is 360. So we know 360 take away 120 is 240 degrees. So I know these 3 segments have to, this arc here and this arc here and this arc here are all going to be congruent, and they all have to add up to 240. So I can divide 240 by 3 and find out that each one of those arcs is 80 degrees. And last but not least, you don't have this on your paper because I didn't want to take up the extra page to Xerox it. But if you can't read it from where you are, it says, "This isn't what she had in mind when Sylvia agreed to join Ed's study circle." And I'm taking it that this lady right here is Sylvia. She's like, what the heck? All right, have fun. Let me know if you have any questions. You can email me. Thanks. Bye.